Hello everyone, welcome to this NPTEL course on computational process design. So in this particular session what we are going to look at is we are going to look at design of batch plants. In the last session we have seen the economic evaluations of the process plants. Okay. So batch plants are extremely important primarily because these are used in the manufacturing of several products like pharmaceuticals, specialty chemicals, etc. Okay. So you can see that each in a batch plant, each batch is processed separately with a defined start and end point, allowing for a better quality control and customization. So if you look at the industries such as specialty chemicals, pharmaceuticals, food, polymers, in this commonly people use the batch plants, batch processes due to their flexibility and adaptability to varying the production needs. So batch processes are ideal for small to medium production volumes and diverse product lines, offering versatility in manufacturing. All products manufactured under the batch are similar in terms of cost, type, consumption of the materials or specifications. So efficient design and scheduling play a crucial role in optimizing resources, reducing production cost and enhancing the overall operational efficiency. Well planned scheduling ensures the timely production, minimizes the downtime, and enables the quick response to the market demands, leading to the improved competitiveness. So you can see that mostly in the polymer productions, mostly in the pharmaceuticals and specialty chemicals, the batch plant is used. Primarily, the main reason is whenever the quality control is an important aspect. In such cases, maintaining the quality in a batch plant is more easy, and therefore typically if you look at the pharmaceutical production, the batch processes are used. Whenever we are using the batch processes, the important aspect to look at is we wanted to minimize the downtime, so make span we have to minimize. Again, we wanted to have the timely production, so tardiness of the product order is uh, minimized. Also the late orders should not be there. Again, whenever there is a change in the market demands, according to market demand, changing things, managing such changes in the batch plants is easy. uh, Also, if you look at the batch plants primarily, so there are multiple orders has to be produced in the same facility, and therefore the scheduling is an important aspect whenever we are designing the batch plants. So single product batch plants, when we are looking at, these are commonly used for manufacturing the specialty chemicals with short life cycles. Manufacturing in a single product batch plants follows a recipe specified by a set of processing tasks with fixed operating conditions and processing times. So the design of single product batch plants involves anticipating operational issues related to the scheduling even when processes are specified through recipes. So even though the recipes are fixed and there is a set processes are outlined for producing a product, still scheduling is an important aspect primarily because multiple equipments which are used in production such uh, product, these are shared between different products, and therefore the scheduling becomes really important. So recipes serve as a standard protocol in the manufacturing of the pharmaceuticals and food items to comply with the regulatory standards. So as specified or as approved by the regulatory board, the same set of process has to be used in the manufacturing of the pharmaceutical as well as in the production of the food items. So even though the recipes are fixed, but you can see that there is a flexibility exists in adjusting the operating conditions and processing durations, particularly concerning the solvents. So when we are looking at the solvents, with respect to the solvent, some flexibility is usually given in terms of the operating conditions and the processing durations. So modification in the operating conditions can be made within the regulatory compliances which are approved. Okay, so whatever the regulatory compliances are there, within those regulatory compliances one can modify the operating conditions. So despite regulatory guidelines, Adjustments to processing lengths and conditions may be permissible under certain circumstances, especially when dealing with the solvents. So only with respect to the solvents, some modifications are permitted. So if you take a simple example here, you can see that this is a simple recipe is given here. So in this case, you can see that the chemical A is first mixed with the B, and then the reaction is occurring here in the reactor. This is referred as a stage 1. So in this reaction, the product C is formed. Then this ABC mixture is then passed to the mixing tank, where another solvent D is added. So by the addition of the solvent D, this entire mixture is then separated in the stage 3, which is a centrifuge, where the liquid A, B and D are separated, whereas the solid C is coming from the bottom of the centrifuge, is then sent to the tray dryer, where the solid dried component C is separated. So you can see that in this particular process there are 4 stages are there. Stage 1, which is reactor; stage 2, which is a mixing tank; then there is a stage 3, which is a centrifuge; and the last one is a tray dryer, which is stage 4. Um, uh, such batch processes is commonly used for production of the drugs, isn't it? So you can see that the drugs can be formed, and then it can be separated, and then it is converted in the form of the powder or the tablets. So with respect to this particular process, the production recipes involve these 4 main pieces of equipment operated in a batch mode: reactor, mixing tank, centrifuge and tray dryer. Additionally, there are some more equipments are there, like pumps and the cooler are there, which operates in a semi-continuous mode within the process, but we have not shown these particular equipments in the we have not included this in the scheduling. Again, initially the production assumes the creation of a single product following a specific recipe outlined below. So in this case, the single product is what we are interested in, and the product is C. So the production recipe here is this: mix raw material A and B in the mixing tank, heat the mixture to 80 degrees Celsius, and allow it to react for 4 hours to form the product C. So you can see that the time required for this particular step is 4 hours. Then mix the resulting product with solvent D for 1 hour at ambient conditions, and then so here in for stage 2, you can see that the time required for the step 2 is 1 hour. Utilize the centrifuge to separate the solid product C from the mixture for a duration of 2 hours. So you can see that in the centrifuge, around 2 hours are required for separating the product C. So time duration here is 2 hours. And the last stage is a drying. So in the last stage, dry the separated solid product in a tray dryer for 1 hour at 60 degrees Celsius. So you can see that here the duration is 1 hour. So each of the tasks described in the processing recipe is carried out in a each of the 4 batch equipments depicted in the figure. I will show the figure, and we can also see the Gantt chart, where how these different units are scheduled in terms of the activities uh, and the processing time. These are represented. So in the Gantt chart, the times for emptying and filling are denoted with a thick lines. However, since these times are typically much shorter compared to the processing times, they are neglected, simplifying the Gantt chart. So what we are saying here is, if you look at the Gantt chart, you can see that this is the Gantt chart for the same process. So you can see that these lines which are shown here, these are for the transfer times. Okay, so you can see that the material from the reactor is transferred to a mixing tank. So these transfer times are also shown here, and you can see that the stage 1, stage 2, stage 4, all 4 stages are represented with the time here. And very often these transfer times are neglected, and in such cases we can simplify this particular Gantt chart to another Gantt chart, where these transfer times are removed here. So you can see that uh, around 4 hours are required in the reactor, plus some transfer times. In the mixing tank, 1 hour is required, plus some transfer time will be required. And then from mixing tank, it is uh, uh, if you look at from mixing tank, it goes to centrifuge, where it takes around 2 hours. and from centrifuge then it goes to the tray dryer where it is around 1 hour is taken. So we have neglected these transfer times, and with neglecting the new Gantt chart is shown here. So with respect to different stages, how different um, stages are performed with respect to the time, that is shown here. So you can see that the efficient operation in a single product batch plants can be achieved by minimizing the idle time. So you can see that if we minimize the idle times of different equipments, we can reduce uh, the we can uh, have the efficient operation of the batch plants, and identifying the bottlenecks in the manufacturing process. So whichever stage is the bottleneck, corresponding to that we can uh, uh, we can change our strategy a little bit to eliminate such bottlenecks, and based on that we can have the efficient operation. So when considering the manufacturing of multiple batches or lots, a critical decision revolves around choosing between the non-overlapping and overlapping operation. So what non-overlapping and overlapping operation is? So when we are having the multiple batches, and if these batches are processed sequentially one after another, then it is called as non-overlapping. So what it means is, the batch 1 is first completed, and after that the batch 2 is starting. So there is no overlap between batch 1 and batch 2. So whenever the production is performed like that, then it is referred as non overlapping. Whereas in overlapping operations, some stages of the batch 2 will start even when the batch 1 is still continuing the processing. Okay, so in a non overlapping operation, each batch is processed sequentially until the preceding one is completed, meaning that the no batches are manufactured simultaneously. Whereas in overlapping operation, efforts are made to minimize the idle times, resulting in the simultaneous production of the batches. This approach aims to maximize efficiency by reducing the downtime. So you can see that the downtime can be minimized with this. So for example, let's say after 7 hours the first batch may have completed the third stage, while the second batch has already undergone the 75% processing in the first stage. So we can see in the figure that uh, I'll show the figure, then you will appreciate. So you can see that this is the non-overlapping operation. Here you can see that the batch 1 is completed around 8 hours, isn't it? Then after, the second batch is started. So you can see that in this case, the cycle time is 8 hours, and downtime, if you consider for two batches, that will be 4 hour. This will be 8 hours and 8 hours here. So the downtime will be 16 hours here. But when we are looking at the overlapping operation, so when we look at the overlapping operation, we can start the second batch just after the operation of the first stage is completed in the reactor, isn't it? So after that we can process the second batch in the same reactor, isn't it? So you can see that with this, the cycle time is now reduced to 4 hours. And if you calculate the downtime will be, in this case, 4 this 4 and this 4, 8, 9, 11, 12. So you can see that the total downtime here is 12 hours, whereas the downtime here is, the max span here is 16 hours. So this is what is written here. So after 7 hours, the first batch may have completed the third stage, while the second batch has already undergone the 75% of the processing of the first stage. This is what happens when we are having the overlapping batches. So you can see that the figure illustrates the efficiency gains of the overlapping operation, showcasing the significantly reduced the idle time. So you can see that in the figure, you can see that this particular unit remains idle for almost how much? Almost 4 hours it remains idle, isn't it? Uh, isn't it? So for almost 4 hours it remains idle here, but in the second stage you can see that we are using this particular thing efficiently here, isn't it, in the overlapping operations. So additionally, figure B suggests that a stage 1 represents the bottleneck in manufacturing successive batches, indicating that the optimizing this stage is uh, crucial for overall production efficiency. Clearly the highest uh, time required, processing time is required, is in the reactor, that is stage 1. So this particular stage represents the bottleneck isn't it? So if we optimize our entire process with respect to this particular stage, then we can have the efficient operation. So the above observations can be quantified with the following definition of the cycle time. So cycle time is represented as the final time minus the starting time Ts. So here Tf and Ts are the initial and the final times of each operating cycle. Now in this case, if we look at the unit 1, so the cycle time with respect to the unit 1 ct1 will be given by what, 8 plus ts1. So ts1, ts2, ts3, ts4 are the initial times at each stage, isn't it? So 8 plus ts1, that is going to be the final time. Remember, if I start from here, isn't it? So the final time will be what, 8 plus this 8 plus the starting time, isn't it? So whatever the time has happened in the previous batch, that will be ts plus 8, and 8 hour after that the new batch can start, isn't it? So in this case, 8 plus ts1 is the final time, isn't it, minus ts1 is the starting time. So if we subtract here, you can see that the cycle time comes around 8 hours. For similarly, for unit 2, unit 3, unit 4, all 4 units we can calculate the cycle time. So cycle time comes around the 8 hours for all 4 units. So here for unit 2, uh, which is the mixing tank, that comes around 8 plus ts2 minus ts2, again 8 hours. For unit 3, which is nothing but uh, the the unit 4, in this case we have used as a centrifuge. So this unit 3 is a centrifuge. So for unit 3, 8 plus ts3 minus ts3, which will be equals to 8 hours. Similarly, for the last tray dryers, the cycle time comes around 8 hours. So you can see that in this case, all stages operate with the identical cycle times of 8 hours. Okay, but when we are taking the figure B, in figure B you can see that uh, the cycle time for the first unit is 4 plus ts1 minus ts1. You can see that here. So 4, and the final, you can see that after this only the second batch is starting. So 4 is the ts plus 4 is the final time, isn't it, minus ts, that gives us the cycle time of 4 hours. So you can see that ct1, ct2, ct3, ct4 all are coming out to be 4 hours here. So clearly the cycle time for the second case is just 4 hours, whereas the cycle time for the first case is where uh, non overlapping operation, it is 8 hours. So from the given example where CT is 8 hours, it implies that the batch is manufactured every 8 hours, and uh, with cycle time of 4 hours, the batch is completed every 4 hours, isn't it? So every 4 hours there will be one batch completion, isn't it? So based on this example, the cycle times for the single product batch plant can be generalized as follows. So we can obtain the cycle time uh, for non-overlapping operation. For non-overlapping operation, we can get the cycle time as summation of tj. So all the stages are there, j stages are there. For all j stages, whatever the processing time is there, summation of all those processing time is going to give us the cycle time when we are looking at non-overlapping operation. But when we are having the overlapping operation, then we are going to look at the processing time of each of these stages, and whichever is the maximum, that will represent the cycle time. So clearly in the non overlapping operation, the cycle time comes around the 8 hours, whereas in the overlapping operation, the cycle time, which is nothing but the maximum processing time of the individual stages, the maximum processing time in this case is a 4 hour for the reactor, and therefore the maximum processing time is giving us the cycle time equals to 4 hours. So it should also be noted that the scheduling terminology, the term max span refers to the total time required to produce the given number of batches. So if we specify the given number of batches, how much time is required to produce those many batches, that refers to the max span. So if we are taking the previous example here, if you look at, if we take the 2 batches to be completed, then the max span is 8 hours, whereas in the second case, when we are taking 2 batches into the account, then the max span is just 12 hours. So this metric, this max span is an important metric primarily because it helps in evaluating the overall efficiency and productivity of the manufacturing process, as it provides the insight into the total duration of the production from start to finish for a specific quantity of the batches. So for a specific quantity of the batches, how much time is required, that we can get, and therefore it provides the information on the productivity of the manufacturing process. Now let's look at the multiple product batch plants. So there are two definitions. Multiple product batch plants involves the production of various products in the same facility. There are multiple products which we are trying to produce in the same facility, often in a sharing pieces of equipment. So multiple products are getting produced, and we wanted to share the equipments between these different products. So there are two definitions. The first one is a flow shop problem, and the second one is a job shop problem. So flow shop and job shop plants are common configurations for multiple product batch plants, each with its own production layout and scheduling challenges. So flow shop plants are where the products undergo the same sequence of operations in all stages, whereas the job shop plants where the products may not require all stages or follow the same sequence of operations. So what we are trying to say here is, when we are looking at the flow shop plants, you can see that all products, whenever we are looking at multi product plants, so all these products are actually following the same sequence of the stages, and same equipments are used sequentially. Okay, whereas when we are looking at the job shop, in a job shop plants, different products, the sequence of the equipment may not be same. Also some of the operations may not be following the same sequence of the operations also, isn't it? So you can see that this is the flow shop plant. You can see that all three products are following the same sequence of the stages 1 2 3 4. In a job shop plants, you can see that it may not be following the same sequence of the operations. You can see that this first one is following 1 2 3 4, whereas the second one is following 1 2 then 4 itself. There is no stage 3 required for the product 2. For product 3, we are starting with stage 4, then stage 3, then stage 1. So you can see that the sequence of the operations are also different, and also some of the operations are not being used whenever we are having the uh, job shop plants. So job shop plants are where multiple products are produced, but each of these products are not following the same sequence of the recipe. They might be using some stages commonly, but some of the stages they may be omitted in the operations. So similarity between the products influence the resemblance of the real plant to either a flow shop or a job shop. Clearly, greater similarity among the products, whenever the products are nearly the same, in that case the plant resembling a flow shop, isn't it? So whenever the products are nearly the same, in that case the plant is flow shop, whereas whenever there is a dissimilarity between the products, it leads to the job shop plants. So flow shop plants are commonly referred to as multi product plants. Flow shop plants are referred as multi product plants, whereas the job shop plants are often referred as multi-purpose plant. So because of their flexibility to handle varying products requirement and operation sequences. So these are some differences between the flow shop and job shop plants. Now let's look at uh, the flow shop plants. A crucial consideration is the type of production campaign employed for manufacturing a predetermined number of batches for different products. It should be noted that for the case of the batch plants with multiple products, it is not generally possible to obtain the closed form expression for the cycle times. So now in this case, both these flow shop plants are given here. You can see that there is a different campaigns are shown in figure 1 and figure A and figure B. So in a figure A, single product campaigns are illustrated. So here in this case, you can see that uh, so there are two type of products are there, A and B. So you can see that initially we are producing only A. You can see that A are getting produced initially, and then B are getting produced. So you can see that this first figure basically represents 3 batches of A followed by 3 batches of B. So all the batches of product A is first completed, and then all the batches of product B are completed. So here you can see that if I look at the cycle time, so cycle time in this case is uh, uh, the cycle time is 25 hours is the cycle time. You can calculate that 5 plus 5, 10 plus 15, then plus 2, so that is 17, and then here 4 plus 4, that is 8. So you can see that it becomes 25. So cycle time is 25 hours, but if you look at the max span will be 29 hours when we are having the single product campaign. Now the another case is mixed product campaign. So in this particular case you can see that product A and product B are getting produced alternately. So you can see that the product A is produced in the stage 1, and the output from the stage 1 is then given to the stage 2, and then it completes here. But once the stage 1 is completed, product B is starting in stage 1, and then it goes to the stage 2. So you can see that A is produced, then B is produced, then A is produced, then B is produced. So in this manner the products are getting produced alternately. So 3 A's and 3 B batches are produced here in this particular figure. You can see that the cycle time is now reduced from 25 to 20 hours, 21 hours. You can calculate the cycle times also here. So 5 plus 2, 5 plus 5, 10 plus 5, 15 plus 6, so that becomes 21. Now in this case the max span will be what? Max span will be again 25 hours. So if we look at, if we analyze these two figures carefully, so you can see that producing 3 batches each of product A and B in plant with 2 stages. One option in flowshop plant is to utilize single product campaign, that is the product A should be completed first, and then the product B should be completed. So all the batches of A are first completed, and then all the batches of B are completed. So alternate is mixed product campaigns, where which involves producing batches according to a predetermined sequence such as AB, AB, AB. So it is important to note that the impact of the max span and the cycle time for different campaign types. So you can see that for a single product campaign we are having a uh, max span of 29 hours and the cycle time of 25 uh, hours, whereas the mixed product campaign, our max span is 25 hours, whereas the cycle time is 21 hours. So but it appears that the mixed product campaign is better, but it is not necessary always. For instance, let's say in the mixed product campaign, you can see that this is the mixed product campaign. Here you can see that after product A, the product B is getting produced in stage 1. So clearly we require a cleaning of the stage 1. Similarly, cleaning of stage 2 is also required, and if there is a significant cleaning or the changeover time is involved, in that case we have to add those changeover or the cleaning time here. And if you take, let's say, a changeover or a cleaning time of 1 hour here, you can see that the cycle time increases from 21 to 26 hours, whereas the max span increases from 25 to 30 hours. So it is not necessary that the mixed product campaign will always give you a better efficiency. It may not be. Again, whenever we are producing a multi-product um, uh, multiple products with the different grades, similar situation occurs. A typical example is, let's say, if you are producing the different grade polymers using different extruder, you can see that you can go from the light color to the dark color easily, but when you are going from dark color to light color, there is a change over time required, isn't it? So all such change over time and the cleaning time has to be accounted when we are looking at mixed product campaigns. So in addition to the product campaigns, the transfer policies are also important here. So what are the different transfer policies that we will look at? There are 3 different transfer policies. So transfer policies in a batch processes determine how batches move between different stages of the production. So the first transfer policy is a zero weight transfer policy. So what it says, immediately we have to transfer the batches to the next stage without any delay. So in a zero weight transfer policy, immediately we have to transfer the batches to the next stage. Again, this particular policy suitable when no intermediate storage is available. So whenever there is no intermediate storage is available, in that case we have to transfer the batch from stage 1 to stage 2, or when holding time further is not feasible. So this particular transfer policy is used whenever there is no intermediate storage is available, or even the holding the product in the batch is infeasible. In such cases we use the zero weight transfer policy. There is another transfer policy which is referred as unlimited intermediate storage. So unlimited intermediate storage means you have the infinite amount of intermediate storage facility available. So whatever the batch you are producing, you can store them in the inventories or in the storage tanks without having any limit on the capacity. So um, such storage policy gives you the most optimum solution, because then you have the higher flexibility, isn't it? Higher flexibility for scheduling, correct? So the third transfer policy is a no intermediate storage policy. So no intermediate storage policy means the batch will not be transferred to the additional storage, but it can remain in the batch itself. It can remain in the original stage itself. So no intermediate storage policy permits holding material inside the vessel temporarily, providing a balance between the immediate transfer and unlimited storage. So the choice of the transfer policy impacts the cycle times in batch processes. So with uh, zero weight transfer typically resulting in longer cycle times, we will see whenever we are having a zero weight transfer policy, typically the cycle time or the max span is higher compared to the unlimited intermediate storage and no intermediate storage policies. So balancing the transfer policies in batch processes is essential to optimize the production efficiency, minimize idle times, and ensure smooth material flow between the stages. So clearly, if you look at optimizing the operation, uh, which policy one should select, it has the significant impact on the schedule. However, there are pros and cons with respect to each of these policies. Particularly if you look at the unlimited intermediate storage, even though it is optimizing the scheduling, but it also increases your inventory cost. So those pros and cons has to be considered while implementing the different transfer policies. So the last point here is the efficient transfer policies contribute to reducing the production lead times, enhancing productivity, and maximizing the utilization of equipment and resources in the batch processes. However, sometimes optimizing one objective is impacting badly on the other objective. For instance, if you are minimizing the lead times by having the unlimited intermediate storage, it can increase the inventory cost. So we can look at this policy little bit in more detail. So you can see that uh, there are two products A and B, and product A requires 6 hours in stage 1, 4 hours in stage 2, and 3 hours in stage 3, whereas product B is requiring 3 hours in stage 1, 2 hours in stage 2, and 2 hours in stage 3. So if we uh, here in a zero weight transfer policy, you can see that zero weight transfer policy, whatever the batch is completed in the stage 1, it has to be transferred to the stage 2. So you can see that the product A, it is transferred from stage 1 to stage 2, and from stage 2 to stage 3. Similarly, now I can start my second product for product B only and only if there is no wait for the stages, isn't it? There is no wait for the different batches. So in this case, I can start only after sometimes here. So then after 3 hours it will be completed in stage 1. Once it is completed in stage 1, it goes to stage 2. So by this time you can see that the stage 2 is still available. So from stage 2, then it goes to stage 3, and you can see that once the stage 2 for the uh, product B is completed, immediately after that the stage 3 is available. So you can see that this particular time is a bottleneck here. So I wanted to have this stage 3 available for product B immediately once it is completed from stage 2. So you can see that in this particular case, if I calculate the cycle time, so cycle time for completing both these products A and B, you can see that the cycle time here is 6 plus 4, that is 10, and 10. Uh, so you can see that in this case 6 plus 4 plus 1, you can see that I can start my um, uh, batch. I can start the product A again in stage 1 at this particular time. So if I calculate the time here, 6 plus uh, 4 plus 1, so that becomes 11 hours. So you can see that the cycle time is 11 hours here. Now let's move to the no intermediate storage. So if we do not have an intermediate storage, in that case what happens is whatever the material is processed, it remains in the stage, that's vessel itself. So you can see that once the product A is completed in stage 1, it is transferred to stage 2, and from stage 2 it is transferred to stage 3, but I can start my product B immediately here. You can see that I can start my product immediately here once the product A is completed in stage 1. I can start my product B in the stage 1, so that goes for 3 hours. After that it can remain idle in the stage 1 itself, isn't it? And once the stage 2 becomes available, this product B is then transferred from stage 1 to stage 2. It remains in the stage 2 for 2 hours. Processing time is 2 hours, but then it remains in the stage 2 for even longer period since stage 3 is not available. And from once the stage 3 becomes available, the batch, the product B is then transferred from the stage 2 to stage 3. So clearly in this case the cycle time is now reduced to 6 plus 3, which is 9. So we have reduced the cycle time from, cycle time here is 6 plus 4, that is 10. So cycle time is reduced to 10 from 11. You can see that we can start the product A again here, so which is after 10 hours. So compared to this, when we look at the unlimited intermediate storage, when we are having the unlimited intermediate storage, that means the material we can take out from the stage and we can store it separately in the storage tank. So you can see that here, uh, when the product B is starting just after the completion of the product A in the stage 1, and then it completes in 3 hours. After 3 hours the material will be transferred from stage 1 to a storage tank. It remains in the storage tank uh, till the point my stage 2 becomes available, and my stage 2 becomes available here. Then this product B is processed in the stage 2 for 2 hours. Then again it will be shifted to a uh, another storage tank. It remains in the storage tank till my stage 3 becomes available, and once my stage 3 becomes available, then it get processed in the stage 3, and that becomes the final product. So you can see that in this particular case my cycle time is further reduced to 9 hours, but in this case we additionally require these storage facilities. Intermediate unlimited storage facilities are required. So you can see that whenever we are having the parallel units or intermediate storage, uh, this can help in improving the efficiency. So parallel units and intermediate storage are strategies used in batch processes to enhance equipment utilization and optimize the production efficiency. So parallel units involve the operating multiple units of the same equipment simultaneously, allowing for the increased throughput and reduced cycle times in the batch process. So what we are trying to say here is, you can see that this particular part is the bottleneck, isn't it? This particular stage 1 is the bottleneck, so I can have the multiple stage 1, so that is something called as a parallel unit. So parallel unit, you can see that, involves operating multiple units of the same equipment simultaneously, allowing for increased throughput and reduced cycle times in batch processes. Again, in intermediate storage tanks, similar to the parallel units, if you are using the intermediate storage tanks placed between the stages in a production process, they can decouple the operations. So you can see that we have decoupled the operation here. You can see that once the batch is completed here, the product B is completed in stage 1, we are storing it in the tank. So you can see that the both these product A and product B are kind of decoupled here now. Now I can use the stored material only when the stage 2 is available. Okay. So parallel units, intermediate storage tanks placed between the stages in a production process decouple the operations, enabling different stages to operate at varying cycle times and batch sizes. Again, the parallel units can be strategically deployed at bottleneck stages to increase the production capacity and reduce the cycle times. This can enhance the overall efficiency of the batch processes. So you can see that whatever the bottleneck unit is there, we can have the multiple such bottleneck units, and with that we can improve the efficiency significantly. So intermediate storage facilities smoother the material flow between the stages, enabling the better coordination of the production schedules and reducing the idle times of the batch processes. Again, same thing can be said with respect to the intermediate storage facilities, where we can reduce the uh, idle times significantly. We can also reduce the cycle time and the make span significantly by using the intermediate storage facilities. So now you can look at the example here. So you can see that here the fermentation process is carried out. So there are two stages are there, stage 1 and stage 2. Stage 1 is taking 12 hours. You can see that after the stage 1, the product is then transferred to a stage 2 where it is taking 3 hours. So you can see that the bottleneck here is the stage 1, which is taking 12 hours. So in this case, if I have to use the uh, if I am not using any uh, uh, if I am not using any intermediate storage, or if I am not using any parallel unit, in that case the zero weight with the zero weight uh, transfer, this is the best schedule we can get. You can see that once the stage 1 is completed, we can start the stage 2 for the stage 1 for the batch 2, and in this manner for these 3 batches, you can see that the max span will be what, uh, 36 plus 3, so 39 hours is the max span here, you can see, and the cycle time is a 12 hours. So now when we are having, let's say, the parallel units, let's say we are having the parallel units in the fermenter. So you can, let's say, if we have a multiple of the stage 1, so if we are having a multiple of stage 1, you can see that we can start the batch 2 directly here. So batch 1 is still under the process. Once the batch 1 is completed, it goes to the stage 2, but there is a parallel unit for stage 1 which can start the batch 2 directly here. So you can see that we can complete the batch 2 almost 50% before the batch 1 is completed in the stage 1. Okay, so once we are having a parallel unit like this, now you can see that my cycle time is reduced from 12 hours to 6 hours. Now in addition to that, if we take a third case where we are having the uh, you know uh, uh, we are producing the larger batch size in the stage 1, but then we are storing that material in a intermediate storage, and from that intermediate storage then we are processing the smaller size batches in the stage 2. So you can see that, let's say, uh, whatever the amount which is getting processed in stage 1 is divided into uh, 4 different parts, and all these 4 different parts are then individually processed in the stage 2. So you can see that in this manner uh, we can efficiently use the equipment, and we can reduce the idle times. You can see these idle times which are here, we can reduce those idle times, which we can eliminate those idle times here in the third case where intermediate storage is there. So the same discussion is written here. The fermentation plant depicted in figure A showcases a significant difference in the processing times between the stages. Stage 1 requires 10 hours, while stage 2 only takes 3 hours. So clearly the stage 1 is the most critical stage here, the rate limiting stage here. So cycle times for each batch in the figure is determined to be 12 hours. That is what we have seen. Given that the stage 1 serves as the bottleneck, a potential solution is to introduce the additional unit in a parallel within that stage, isn't it? So that is what we have done here. We have added additional stage 1 unit here, and because of that now cycle time is reduced from 12 hours to 6 hours. So with this inclusion of this extra unit, the plant's operation can be modified, which is shown. This adjustment results in the reduced cycle time of 6 hours. And whenever we are having such additional parallel units, we can calculate the cycle time by using this particular equation. So where you can see that the equation for cycle time with zero weight transfer and parallel unit is given. So let's say NPJ is the number of parallel units, and in that case we can calculate the CT as maximum of Tij divided by Npj. So here Tij is the individual processing time of each unit. So clearly divided by Npj, here Npj is the number of parallel units. So you can see that the 12 was the processing time, maximum processing time for stage 1, divided by the number of parallel units are now 2. So 12 divided by 2, so that becomes 6. So our cycle time comes out to be 6 here. So when aiming to produce a large number of batches, it is important to consider optimizing the batch sizes. So batch sizes, whenever we are trying to produce large number of batches, optimizing the batch size is important, primarily because based on the batch size, the equipment size you can design. So by reducing the cycle time to half, the batch sizes can be reduced from 1000 to 500 kg while maintaining the same overall production output. Okay, so clearly you can see that the batch sizes, uh, by reducing the batch sizes, we can again further reduce the equipment size. So another option involves introducing the intermediate storage between the stages. So you can see that the third case which we have seen here, where the intermediate storage we have added. So now in this particular case, uh, the third case is what? In the third case, we are introducing the intermediate storage between the stages, providing the flexibility in the operations. So this approach decouples the two stages, isn't it? Once we are having the intermediate storage, now we have decoupled both stage 1 and stage 2, and we can have a different cycle times for both stage 1 and stage 2. So that is what we are doing. In stage 1, the cycle time is 12 hours and can handle the batches of 1000 kg, let's say, while the stage 2 has a cycle time 3 hours and can handle 250. So you can now see, 10,000 kg we have produced in 12 hours, we can store it in the intermediate storage, and from that intermediate storage 250 kg which we are going to fit to the stage 2, and you can see that within the same 12 hours this 254 times we can put it into the stage 2. So you can see that the idle time for the stage 2 has reduced significantly. Now you can see that the batch size for the stage 1 is 1000, whereas the batch size for the stage 2 is 250. So we can have a different batch sizes when we are having the intermediate storage. So again, the every batch produced in stage 1, the 4 batches will be produced in stage 2 in this particular case. So in this scenario, it is evident that the intermediate storage needs to accommodate up to 3 batches, ensuring the smooth operation without the idle times. Okay. So sizing of the vessel, clearly once the batch size is fixed, then we can calculate the sizes of the vessels required in different stages. So sizing of the vessels in batch plants is a critical aspect of designing the efficient production process to meet the production demands and optimize the resource utilization. Specific volume factors, denoted as a size factors, are used to determine the required vessel volumes for producing a unit of final product in each stage of the batch processes. So size factors are calculated based on the specific volume of the mixture in each stage, considering the density of the mixture and the weight of the final product. So you can see that if the density is given and the specific volume we can calculate for the mixture in each stage, using the specific volume and the density of the mixture, we can calculate the size of each of these vessels which are used in different stages. We can see the case study here. So let us consider a two-stage plant aiming to produce 5 lakh kg per year of the product C. The plant operates around 6000 hours annually, and the below outlines is the recipe for the manufacturing of the product C. Remember, in the batch plant the recipe has to be provided. So here in this case the recipe is given for the production of C is combine 1 kg of A with 1 kg of B, then undergo 4 hours reaction to yield product C. The resulting yield is 40% by weight, 40% by weight. So whatever the total weight is there, of that 40% by weight is the product C, with a mixture density denoted as, so mixture density after the unit stage 1 is 950 kg per meter cube, whereas in the stage 2 what we are doing is we are introducing the 1 kg of the solvent, and then we subject the mixture to a centrifugation for 1 hour to retrieve 93.75% of the product C. The mixture density in this particular case is 1000 kg per meter cube. Now we wanted to calculate what should be the size of the vessel which is required in stage 1 and stage 2. That is what we are trying to calculate in this particular case study. So you can see that in this particular stage 1, 1 kg of A is added, 1 kg of B is added, so the total amount becomes 2 kg. Out of 2 kg 40% is the weight of the C, so that will be nothing but what, 0.8 kg of C we will have, and the remaining 1.2 kg will be the unreacted A and B. Now these are then given to the stage 2 where 1 kg solvent is added, so the now total weight becomes what, 3 kg. Out of that you can see that out of this 0.8 kg C, in the problem it is given that 93.75% of the product C will be retrieved. So 93.75% of 0.8, that becomes 0.75 kg of C. So 0.75 kg of C is going to be will be retrieved from the separation unit here, and whatever the remaining is, that is 2.25 kg, that will be A, B and the solvent. So now in this particular case we wanted to find out the size of the stage 1 and as well as size of the stage 2. So the size factor Sj for each stage J is nothing but what, volume of the vessel J required to produce 1 kg of the final product. Volume of the vessel J required to produce 1 kg of the final product, that is what is defined as the size factor Sj. So in this case specific volume for the stage 1 is what, here the density of the mixture coming out from the reaction stage is given, that is 950. So 1 by 950, that gives 1.0526 into 10 raised to power minus 3 meter cube per kg of the mix. That is the specific volume for the stage 1 we have obtained. Now this specific volume multiplied by the total weight divided by what is the weight of the final product, that gives us the S1. So S1 is nothing but volume of the vessel J required to produce 1 kg of the final product. So how much is the amount of the final product is produced, which is 0.75 kg per C, isn't it? So this is the specific weight we have obtained for 2 kg of the mixture coming out from the reaction stage. So in this case S1 will be given by what, the specific volume multiplied by 2 kg, so 2 divided by the final weight of the final product, that is 0.75 kg. So it becomes 2.807 into 10 raised to power minus 3 meter cube of the production per kg. So this is the S1. Similarly for stage 2, again the density is given, which is 1000 kg per meter cube. So we can calculate the specific volume, that is comes out to be 1 by 1000. So that is nothing but 1 into 10 raised to power minus 3 meter cube per kg. Again we can calculate S2. S2 is nothing but the size factors. So size factor S2 for the second stage can be obtained as the specific volume multiplied by the total weight divided by the weight of the product. So total weight in this particular stage is what, 3 kg, isn't it? 2, 1 plus 1 this and the third one here. So this is the total weight is going to be 3 kg, and out of this 3 kg how much is the product? 0.75. So 3 divided by 0.75 into the specific volume, that gives us the S2. So S2 comes out to be 4 into 10 raised to power minus 3 meter cube of the production per kg. Now we know S1 and S2. Based on this S1 and S2 we are going to calculate the sizes. Now in this particular case in the problem what is given is 1 unit per so if we use 1 unit per stage and operate with zero weight transfer, the cycle time in this case is given as, so let's say reaction is taking place for 4 hours and the separation is taking place for 1 hour, so cycle time in this case will be 4 hours, isn't it? So maximum between the processing time of individual unit, that is nothing but the cycle time. So cycle time in this case comes out to be 4 hours. Now in the problem what is been given is there are 6,000 hours we wanted to operate, isn't it? 6,000 hours we are operating, so how many batches we can produce? 6,000 divided by 4, isn't it? So 1,500 batches we can have, correct? And 1,500 batches we can have, but the total amount of the production is what? 5 lakh kg, isn't it? So 5 lakh kg divided by the number of batches, so that gives you the amount which need to be produced in each batch. So in this case you can see that 333 kg we have to produce in each batch, so batch size is 333 kg. Okay, now with this batch size, now we can obtain what will be the size of the stage 1 and stage 2. What will be the size of the vessels in the stage 1 and stage 2? So batch size multiplied to a the size factors, that gives us the volume of the vessel required in size for the stage 1. So stage 1 volume of the vessel required in stage 1 V1 is given as S1 into B. S1 we have already calculated, so S1 comes out to be 2.807 into 10 raised to power minus 3, that multiplied to the batch size which is 333, so this gives 0.934 meter cube as a size for the vessel 1. Similarly, we can calculate the size for the vessel 2, which will be given as S2 into B. So in this case 4 into 10 raised to power minus 3, that is S2, multiplied by 333, that becomes 1.332 meter cube. So this is what we have obtained. These are the volume of the vessels required for stage 1 and stage 2. Now you can see that the stage 1 is the bottleneck because it is taking the more amount of time. So we may contemplate deploying 2 units operating in parallel, isn't it, but out of phase. So we wanted to have these 2 units working out of phase so that the cycle time can be reduced. So in this case the cycle time will reduce from 4 to 2, isn't it? So the cycle time for the stage 1 will reduce to 2. This implies that we can have produced twice as many batches, isn't it? So we can reduce the batch size for unit 1. We can reduce the batch size for unit 1. uh, uh, we can have 3,000 batches. We can have 3,000 batches, or we can reduce the and also we will be reducing the batch size to 166, which will be half of that, isn't it? So in this case you can see that if the batch size is half to 166 kg, the size of the vessel in the stage 1, that will also reduce. So size of the vessel in stage 1 will be reducing to 0.467 meter cube, whereas for the vessel 2 it will be 0.666 meter cube. So you can see that based on whether we are having the zero weight strategy, zero weight transfer strategy, or whether we are having the parallel units, based on that the size of the vessels we can determine in this particular case. Now the another interesting concept which we have to look at is the inventories. So inventories play a crucial role in batch processes, influencing the production cycle, times, resources utilization, and operational efficiency. You can see that the inventory, so see, if we are storing everything in the inventories, it incurs the inventory cost, isn't it? And if we are having the zero weight uh, transfer, in that case we don't require inventory. In that case, whatever the product which is produced in stage 1 is transferred to the stage 2 immediately. We don't require inventories in such cases. So clearly in that case we don't require the inventory cost. So the selection of the production cycle in batch design involves the trade-off between the transition, cleanup times, and inventory levels, impacting overall process performance. So shorter production cycles reduce the need for carrying the large inventories by producing products more frequently, but may increase transition times, affecting the overall efficiency, isn't it? Again, the longer production cycle decreases the transition times, but then we require the higher inventory levels as products are produced less frequently, and therefore these products has to be stored in the inventory, impacting the resource allocation and the storage requirements. So managing inventories efficiently in a batch process involves considering the factors such as production demand, cycle time, storage capacity, and material flows to ensure smooth operation of the resource optimization. So clearly, what inventories, what size of the inventories we should be having, all these have the impact on the production efficiency, and managing the inventory is also a important aspect in the optimizing the process. So analyzing the inventory profiles helps in understanding the impact of production cycle length on the inventory management, identifying the opportunities to optimize the inventory levels and the production schedules. So clearly, we have to maintain the inventory profiles, and whatever the inventory profiles are, based on that we have to obtain the production schedule, optimize production schedule. Now let's look at the synthesis of the flow shop plants. So synthesis of the flow shop plants involves generating and evaluating the various alternatives to design efficient production systems in batch processes. So a key objective of the synthesis is to explore different configuration of the equipment and processes to identify the most cost effective and operationally efficient design for batch production. The number of potential alternatives in flow shop plant synthesis can be extensive, requiring systematic optimization approaches to evaluate the economic trade-off and performance metrics. So you can see that there are multiple objectives are involved and multiple alternatives are involved whenever we are looking at the synthesis of the flow shop plants. So clearly, which alternative should be used depending on whether you are interested in minimizing the max span, whether you are interested in minimizing the late orders, whether you are interested in minimizing the tardiness. Based on that, different alternatives we can get. So again all these alternatives will have the implication in terms of the cost. So net present value is commonly used for economic evaluation in the flow shop plant synthesis, considering the factors such as revenue, investment cost, operating cost, inventory cost, interest rates, project life, tax rates, and salvage value. So you can see that net present value we can calculate using this particular equation, and then based on the net present value we can select the alternatives here. So you can see that here R is the annual revenue of the products, CI is the investment cost, CO is the operating cost, uh, C in INV is the inventory cost here. I is the interest rate, N is the length of the project life, TX is the tax rate, and S is the fraction of the investment for the salvage value. So with this, we can calculate the net present value for different alternatives, and based on that, we can select the best alternative of the flow shop plant. So again, when we are trying to select the best alternative, there are different aspects while making the decision. So there are three major decision levels involved in a batch processes and their corresponding items as given here. So the first level is the structural level. In the structural level, the assignment of the task to the equipment. So actually it involves the determining how different tasks or operations are allocated to the specific equipment or processing units within the production system. So multiple tasks are involved in the one unit, or only single task is involved in the one stage. This type of decisions we have to make in the structural level. Also, how many number of parallel units or intermediate storage are available. So this refers to deciding on the utilization of parallel units, multiple units operating simultaneously, and also how many intermediate storage facilities are there to optimize the production efficiency and the resource utilization. So these decisions has to be made in the structural level. Then the next one is, once these decisions are made, based on that we can calculate what will be the batch size. Once the batch sizes are there, then we go for the equipment sizing. So equipment sizing level is nothing but what equipment sizing is calculated. So in this case, we determine appropriate size and capacity of the equipment and processing units based on the production requirements, batch sizes, and operational constants. So the same way, the way we have calculated the size for the vessels in the illustrative examples, in this manner we can calculate the size of different equipments required in different stages based on the batch sizes, different constants and production requirements. The next is the scheduling level. Once the sizing and the structural level is done, then how we are going to allocate different equipments for different tasks, this is something which we call it as a scheduling. So in this particular case, the nature of production campaigns, so whether we are having the sequential single product uh, campaign or multi product campaign is there, that we have to select. What are the transfer policies we are looking at? It is whether it is a zero weight transfer policies, whether it is a infinite storage uh, uh, policy, or whether it is the non uh, uh, immediate storage facility. So all these uh, transfer uh, uh, policies also have the impact on the schedules. So all these policies are utilized in the problem formulation, and based on that we obtain the optimized schedule, uh, which can use the resources in the most judicious manner. So then the next important aspect here is the length of the production cycle. So here we are trying to minimize the production cycle. So considering the factors like batch processing times, inventory management, and production efficiency. And the third important decision we have to make at the scheduling level is the sequencing of the products. So whether we will have all the um, uh, product A should be sequenced first and then the product B should be sequenced, or it should be alternate product. All these decisions we have to make it here. So involve establishing the order in which the different products are processed within the production system to maximize the throughput, minimize the idle times, and optimize the resource utilization. So basically what we are trying to say here is, in the last point, is nothing but, so you can see that in this particular case, uh, we are having this multiple products are there. So you can see that the single product campaign, we are having only the product A is getting produced first, and then we are producing the products in the alternate way, like AB, etc. So which product campaign should be selected, that is what we are discussing in the last point. Okay, so now again, in order to synthesize the flowchart plans at the structural level, assigning the task to the equipment stands out as one of the decision with the most significant implications for scheduling and economics. Primarily because because based on how many vessels you are making for different tasks, based on that the capital cost will be incurred and also the operating cost will be there. So you can see that in this case, let's say there are four tasks are there. The first task is the mixing, which is taking place for 2 hours. Then the task 2 is there, where the reaction is occurring. Task 3, again the mixing is occurring, and in the last task the reaction is occurring for 2 hours. So if you look at the Gantt chart for this process, the Gantt chart is showing here the cycle time here can be 4 hours, because the maximum processing time is taking place in the reactor. So you can see that the maximum cycle time we can have 4 hours. But now uh, so in this case you can see that the assigning each task to the dedicated processing equipment as depicted in the figure is the simplest approach. Mixing task occurs in the basic vessels with the agitator, while the reaction takes place in the jacketed vessel, except for the uh, second reactor made up of the stainless steel. The remaining units are of the carbon steel. The cycle time in the figure is 4 hours, assuming the zero weight transfer. This is what we have seen here. Here the cycle time will be 4 hours in the zero weight transfer policy. Now we can modify this particular process, isn't it? And we can say that the task 3 and 4 we wanted to do it in one vessel itself. So in that case you can see that if you do that with this particular case, my cycle time is still remains 4 hours, isn't it? Cycle time remains 4 hours, but the number of equipment I have reduced. So here the simplest rule is to, whenever we are synthesizing the flowshop plant, the simple rule here is merge the adjacent task whose combined processing times do not exceed the cycle time. So you can see that I can combine these two stages, mixer and reactor, which are incurring 2 hours and 1 hour, so that becomes 3 hours, and this 3 hours is less than the cycle time of 4 hours, so I can combine these two in the last reactor itself. So with this you can see that we have reduced one equipment, and also uh, the because of that the capital cost will be reduced. But let's say we can, there is another options available, like we can combine all these 4 tasks in one unit, but in that case you can see that the cycle time will be 9 hour. And so unlike the previous case where the cycle time was remaining 4 hours, in the next case the cycle time is increasing to 9 hours. So clearly the third alternative is not giving advantage in terms of the cycle time, but it is giving the advantage in terms of the equipment required. So all the stages are carried out in only one reactor, whereas the cycle time is now increased from 4 hours to 9 hours. So based on the cost calculation, then one has to select which alternative is useful in this particular case. So these are the different alternatives and different uh, uh, options available when we are synthesizing the batch plants. It could be based on what type of transfer strategies, policies we are implementing, whether we are having the multiple units are there, or whether we are having the intermediate storage or not. Based on that different alternatives are possible, and the best alternative one has to select based on the cost calculation. So we stop here, and we will continue with the modeling of the process flow sheet and the optimization in the next session. So thank you all.